Okay, so let's start. So I'm Louise Darico. I'm going to talk about a bit of my work from my postdoc research, which are focusing on exploring radionuclide contaminations using a new radium standard and NanoSIMS analysis. So I'm going to give you a bit of context for this work. We are in the context of management of radionuclide contaminated site. So for a bit of history, for French uranium ore, it was exploited from 1948 to 2001 with extraction and exploitation of the uranium ore, which led to, of course, the production of uranium concentrate and as well waste rock and tailings. During those extraction and exploitation, some contamination could have occurred, leading to enriched radionuclide in some environment, such as sediment, soil, wetlands. And when we manage those sites, there is a lot of questions, and we are here going to focus on two main questions, which is what is the source of the radionuclide in this environment, and what are the stability of the bearing phases of this radionuclide. So when we want to look at the origin of radionuclide, and in the case of uranium mining activities, we can use stable lead isotopes and the ratio of lead isotopes, for example, and also we can look at radioactive disequilibria. So for example, for the uranium decay chain, we know that uranium is more mobile than some of its decay products. So we can look at some radioactive disequilibria between radium and uranium or radium and thorium and see if there was a mobility of some of those elements. Most of the time we do bulk analysis. So we take the whole sample, so the whole sediment, the whole soil, and we look at isotopic ratio and look at disequilibria. But we can have a loss of information when we look at the bulk. For example, if there is dilution or isotopic mixing with the weathering of the crust, especially if we have really low concentration. And also when we do bulk analysis, we do not have access to specific information such as what is the nature and the stability of the bearing phases of the radionuclide. So the objectives was to obtain a quantitative imaging of radionuclide, isotopic ratio, so we wanted to look at the ratio, but at the submicrometric scale, so at the grain scale, really we are looking at the mineral. So for this, we wanted to look at some radioactive element, for example, uranium-238, thorium-232, thorium-230, and radium-226, as well as some stable elements, such as the lead isotope. So to identify the origin, we are looking at some isotopic ratio, so the 3 here, for example. And when we want to, we wanted also to understand the mechanism of incorporation and release of some radionuclide within a given phase. And for this, we wanted to look at the radium and uranium ratio, as well as radium and thorium ratio. So the objective was also to identify some process that governs the dispersions of those radionuclide in the environment. So for this, we identify the bearing phases of the radionuclide using SIMS analysis, so mostly uranium bearing phases. And also we looked at the isotope distributions using NanoSIMS. So for this work, we needed to do a bit of analytical development. Here to show you, we used some standards to do an instrument calibration for some of those isotopes, and we wanted to use really the matrix that are the most similar to what we could have in environmental samples. So for example, for uranium and thorium-230, we use nautunite minerals. If you want to have a bit more detail for this calibration, you can see the work of Teten from this year, and there is a paper from Jérôme Alléon, which should be coming soon. Also, for lead isotope, we use some NIST standard, and then for radium, we use some synthesized barite that I'm going to present you in the next slide. For the settings, for the NanoSIMS, so we use a Chemical NanoSIMS 50 instrument, the one from Muséum National d'Histoire Naturelle, so in Paris. And we use a combination of multi-collections with peak jumping. So we used an oxygen primary ion beam, and we could achieve a spatial resolution of 0.7 micrometer. So here, just to resume what we used for the trolley. So the first one we used for barium. The second one we used for the 3 isotope of lead, so 206, 207, 208. The third one for radium, and then for fourth one for thorium that we looked at the oxides. And then, at least for the uranium, we looked also at the uranium double oxides. Again, if you want more details, you can see Teten paper from this year and the following paper from Jérôme Alléon. So for radium, we needed to do our own standard because we didn't have any. And we also wanted to look at some interference that we could encounter in some environmental sample. So, for example, the barium strontium complex, but also the lead oxide from 208 lead 18 oxide, which is really close to the mass of radium. So what we did, we synthesized 2 barite enriched in radium. The first one with up to 9 ppm of radium, and the second one with 3 ppm of radium. And in this one, we also have strontiums. So it permits us to look at the interference of barium strontium on the radium signal. And to study the lead oxide interference, we used a plugongumite mineral. So it's a lead and aluminum phosphate, really enriched in lead naturally. That is present in a lot of environments such as sediment and soil, so really a common mineral. And we also wanted to access how much the content of lead could impact the signal of radium. So we also synthesized 3 barite, this time enriched in lead, so with 3 different concentrations. So here, the results. So I'm showing you the intensity of the signal for the mass around radium. So first, here in green, we have the signal for the barite only enriched in radium. So we have the signal of radium here. And for the standard enriched in radium and also with strontium, we can see here the signal of the barium strontium complex here, but we can really distinguish. They are really distinct from each other. This signal is really distinct from this one. And for the lead oxide, so we looked at the plugongumite, which really have a lot of lead in it, and we can see the signal of the lead oxide complex compared to the radium one. So we can really distinguish the two in this setting, so with the resolutions that we could access. But we wanted to see if there was an impact from the tail here from this signal. So we did some analysis at this mass. So for radium, we selected this mass, and we looked at the impact of lead on the signal. So here you have the signal at the mass selected for radium, and here you have the content of lead in some standards. So we have a blank here with no lead, and we have here 3 different barite enriched in lead, so with 3 different content of lead. And here we have also the signal for the plugongumite, so the one we where we can see the really lead oxide signal. And as you can see, we do not have an impact on the radium signal. We see no correlation with even a lot of lead. So when we select when we really select the good radium signal, so we do a really good selections and a really good identification also of the signal, we can see that we do not have an interference linked to the lead presence. So we know we are looking at radium. We know we don't have an interference on the signal. So here, a bit of example of what the image we obtained for the barite standard. So here is for the standard with 9 ppm of radium. You have here the image for barium, and here the image for radium. So we really have a signal for radium. And I'm showing you also how we selected some region of interest to study the reproducibility of the standard and also the homogeneity. So here we selected some area and we looked at the radium-barium ratio. So we compare the ratio, radium-barium, along 3 analytical sessions of NanoSIMS, so one from January, one from June, and one from October, so it's from last year. So here is the result from the standard enriched with 3 ppm of radium, and here for 9.65 ppm of radium. And as you can see, we have really a good reproducibility along the sessions with 16% of variability for this standard and for only 7 for this one. So really great reproducibility for the 3 sessions. Sorry. And we also wanted to see if we could use this standard for quantitative analysis. So we compare the radium-barium ratio of the standard B against the standard A. And we compare it also to the radium concentrations, so the one we know because we synthesized it, so the standard B against the standard A. And we obtain really similar results with the value overlapping with the uncertainty. So it shows that we have a consistency and a coherence with the concentrations that we know we have in our sample, in our standard. So this confirms that we can use this standard for radium concentrations by NanoSIMS measurement for barium, yes. So we also were able to obtain a calibration curve. So we looked at the ratio of radium and barium compared to the concentrations of radium in the standard. So we know we are looking at radium, we have a standard of radium, so we wanted to do an application on field sample. And for this, we selected the study site of Raufin, which is a wetland located in the Puy-de-Dôme, Auvergne-Rhône-Alpes, so in France. And this wetland is located near a former mining site, so uranium mining site, and processing sites. And we know that there is a significant accumulation of radionuclide in this wetland, which is linked to tailing deposits. So during the process of the uranium ore, there was a tailing deposit in this wetland. And you can see them, these deposits on the soil core. So the white, orange, and gray layer are tailing deposits. And we know that there is a really great diversity of radionuclide-bearing phases. So we know radionuclide are linked to organic matter, iron and manganese oxide, phosphate, sulfate. So really great diversity. We also know that there was a treatment of 2 uranium ore in this site. So the first one was Parson site, which is a lead and uranium phosphate. And the second one was pitch blende, so a uranium oxide. So to study the bearing phase by NanoSIMS, we selected 2 samples. I'm going to show you results for 2 samples. The first one was the topsoil of this core, which is really enriched in uranium, as you can see here, and also in radium. So we were really hoping to see radium images by NanoSIMS. And also we study a sample directly. So here, the white deposit that you can see here is a tailing really near the stream in the wetland. And we selected a sample from here too, which have high content in uranium and in radium. If you want more information on this site, you can see all these papers that study uranium and radioactive element in this site. And well, there is really a lot of information if you want. So we did a lot of SEM analysis, and we selected some uranium-bearing phases mainly. Here is an example from an autunite-like minerals. So autunite is a phosphate and calcium uranium phase. And here are the results for NanoSIMS image. So we have uranium here, the lead isotope here for 208, 207, 206. And here we have radium and thorium-230 and thorium-232. As you can see, for radium and thorium for this phase, we don't have a really high signal. We only see a bit of dot, but it's still greater than the instrumental noise. Another example here for an iron manganese oxide, we have here the uranium, the lead isotopes, thorium here for 230 and 232, and here for radium. And I hope you can see here we have a bit of an accumulation maybe of radium in this phase compared to uranium, for example. So it could be really interesting to look at the ratio between radium and uranium in this phase. That could give us a bit of information maybe. And last one, for example, we have a parsonsite-like mineral. So parsonsite was a uranium ore that was exploited at the Rofin site, so really close to the primary mineral. And we have here the uranium signal, which is really high, the lead isotopes also, and for radium here and thorium here, we have really a great image and maybe higher content in radium in this phase. So we have a lot of different phases that we observed, and we can then access a bit of more information when we do some isotopic ratio. So I'm going back to my lead isotope ratio for here 208, 207, 206, and we can compare the isotopic lead ratio of the phases that we observed to the parsonsite and pitchblende ore, so the two ore minerals that were processed at Rofin, and we can put them on a mixing line between these two uranium ores. So here we have the pitchblende one, and here we have the parsonsite here, and we can see that most of the phases that we observed are really close to the parsonsite one. So if I zoom in, we see we are along the line for some of them, and we are really close to the parsonsite pole here. What we can see also, if there is, we're not only on the lines, so maybe we have different origins of these phases. We could wonder if some of these phases are inherited from the primary ore, so from the parsonsite treatment, but we can also wonder if some of these phases are secondary one. So some phases could have reprecipitate in the soil within the wetland or during the treatment of the ore, for example. And what we want to do, what we want to be able to do, is to link the origin of these phases to maybe some mobility of uranium or radium. So to look at this, we wanted to obtain the radium and uranium ratio for those phases, but also the radium and thorium ratio. So for this, we can use the Limage software. we can give us the ratio of those elements and give us the image of the ratio. But as you can see, for radium and thorium, we still have really low signal. So when we do the ratio of two elements with really low signal, we obtain images that are a bit difficult to interpret. And with here, we don't have enough data. So we wanted to try a bit of data treatment. So for this, we use geostatistical tools. And we worked with geovariance, develop a software which is Isatis Neo. And we were able to use a lot of geostatistical tools. So I'm not going to present you everything we tried, but here is ordinary kriging and ordinary kriging factorial. And we did the same as in image. So we did the ratio of radium and uranium, and here for radium and thorium. And we obtain a great image, as you can see here, with maybe a better resolutions than what we can obtain with l'image here for this ratio. But as you can see, for radium and thorium, still we don't have enough data, in fact, to obtain a better image. It's still a work, it's still an ongoing work. We are hoping to look at different tools and maybe obtain a better data treatment. But still, l'image is still good because when we looked at the ratio obtained with geostatistical tool, the uncertainty associated with the ratio is greater than the one that we obtain with l'image. So for interpretation of the data, it's not really good for us as a geochemist. We want to have the least uncertainty on the ratio to be able to tell something on what happened in this environment. But it's still an ongoing work, so I hope we can find something that really will work for us. And I'm going to conclude for this work. So we did synthesize some radium standard, and we could validate their reproducibility. We confirm the absence of impact of interference, and we also were able to create a calibration curve for radium content in barite. And we could validate the feasibility of analyzing multiple radionuclides in some environmental sample. So it can give us access to more interpretation of the origin of radionuclide. And we saw that, for example, for the lead isotope ratio, most of them are in accordance with bulk results, so from former study. And maybe we can see some primary phase and secondary phases for some of those results. So still an ongoing work, but we are trying to use some geostatistical tools, and maybe we can see potential structural feature for some phases, or even give us access to better images of the ratio. So that's it for me. Thank you for your attention and for listening.
Thank you very much again to all of you for your time. We hope you have found this presentation enriching and insightful. A special thanks to our speaker, Louise Darico, for sharing such interesting work with us.